Continuing with the fourth lecture in the series of electrostatics, uh, possibly the last lecture, we'll have to do four proofs here. So, starting with the first proof, derive an expression for a couple acting on an electric dipole in a uniform electric field. So, as you can see, we have electric field E acting from the left hand side of the page towards the right side. I have got two charges A and B, which are separated by a distance 2L. The distance is intentionally taken as 2L by convention, if you remember from previous chapters. Okay. Now uh, the axis of the dipole is making an angle theta with the direction of the electric field. This is the angle theta we are talking about. And then obviously the force acting on A would be minus QE bar, which is highlighted here, and force acting on B would be plus QE bar, which is duly noted here. So FA is equal to minus QE bar and FB is equal to plus QE bar. Now F A bar is equal to minus FB bar. Okay, that is obvious. They are two equal and opposite forces, and they are separated by a distance. They form a couple, and any couple will develop a torque. Now, therefore, torque, which is tau bar, would be equal to d bar cross f bar. Okay, d bar cross f bar, where d is the perpendicular distance between the two opposite forces. So magnitude of the torque tau bar is basically tau, and that would be equal to 2L QE sine theta. Okay, 2L sine theta is the perpendicular distance, F is equal to QE is the force. Okay, yes. Now this uh, uh, 2L into Q is electric dipole moment P, but P is equal to Q into 2L, electric dipole moment. Okay, therefore magnitude tau would be equal to PE sine theta, which if we would write in a vector form, that would be tau bar is equal to P bar cross E bar, P bar cross E bar in vector form. If theta is equal to 90, then tau is equal to PE, theta is equal to 0, then tau is equal to 0, which basically means ki torque tends to align its axis along the direction of the electric field. I'll write this in a colored. Yeah. The torque tends to align its axis along the direction of electric field. Okay. Tau bar is equal to P bar cross E bar. Let us derive an expression for the electric intensity at a point on the axis, which is point P here, on the of an electric dipole. The electric dipole is obviously AB here, charge plus Q at B and charge minus Q at A. Now, let the uh, point P be separated, be placed away at a distance r from the center of the dipole. So I'll start off with writing that. Let P be a point at a distance r from the center. From the center of the dipole. Now, at P, there will be two electric fields which are interacting. Electric field due to B and electric field due to charge minus Q at A. So, basically, we are looking at EB plus EA. Okay. What would be electric field intensity at P due to the charge minus Q at A? So that would be EA bar, and my EA bar would be equal to 1 by 4 pi epsilon 0. Charge on A is minus Q upon distance is R plus this distance L. Okay, so it's going to be R plus L the whole square. Please note this, R plus L the whole square into unit vector in the direction PD, PD cap, because the electric field is going to act in this direction at point P. It's going to pull it back negatively. Okay. Similarly, EB bar, which is closer, that would be equal to 1 by 4 pi epsilon 0. Charge here is plus Q. So plus Q upon R minus L the whole square, because here L is reduced. This L is reduced from the whole distance R. Okay. Please note this. It's very important because the whole proof depends on this. And then, of course, my unit vector PQ cap. Now my net resultant field at P on the axis due to the dipole is going to be EB bar plus EA bar. Okay, and of course, so magnitude of EA bar, we are not worried about the direction at the moment. That would be equal to sum of the magnitude. So it would be 1 by 4 pi epsilon 0 Q upon R minus L the whole square plus, oh no, minus Q. So it would be minus Q upon R plus L the whole square. In fact, I'll take the Q outside. Q by 4 pi epsilon 0, and if I do the LCM, I'll get R plus L the whole square minus R minus L the whole square upon R square minus L square the whole square. Okay, because it is R plus L into R minus L, which is R square minus L square, but then this whole thing is squared, so it is R square minus L square the whole square. Now a little bit of 9th standard algebra, 4 pi epsilon 0. We know that a plus b the whole square minus a minus b the whole square is 4ab. So it's going to be 4rl upon r square plus l square uh, the whole square. ठीक है. So a quick simplification there. So a little bit of rearrangement would give me EA is equal to 2 into 2 LQ into R upon 4 pi epsilon 0 R square minus L square the whole square. Okay. Now 2QL is P like last time. But electric dipole moment P is equal to 2QL. Okay, therefore substituting you will get EA is equal to 1 by 4 pi epsilon 0 uh, 2PR upon R square minus L square the whole square. Okay, so this is the expression for magnetic field intensity on a axial line, in a straight line. If you are there, then this is the condition. Now if we use a short dipole, R is much greater than L, therefore uh, uh, L square uh, can be neglected compared to R square. So I'll get a nice jugaad. EA would be equal to 1 by 4 pi epsilon 0 2 PR upon R square the whole square. Now R cancels with this to give me 1, and the expression becomes EA is equal to 1 by 4 pi epsilon 0 2p by r cube. Okay, 2p by r cube. This expression, simplified expression, is used in numericals, but remember this formula to be used only if it's a short dipole, where it is given that it's a short dipole. If it is not given as a short dipole, please use the original formula, which is a little bit complicated. Okay, so please note the short dipole correction, but most of the times they would give a short dipole, so not a big problem there.